right, we're moving on to activity 2-3, using structure to find solutions. So the directions say, here are some equations, we've got 8 of them, that contain a variable and a list of values. That's down here at the bottom. I've got a big string of them, kind of like a word bank, but with numbers. It says, think about what each equation means and find a solution in the list of values. If you get stuck, draw a diagram. Be prepared to explain why your solution, why your solution is correct. So some of these you might be able to just solve, find the solution for just by what we call by inspection in math. You can look at them and using your knowledge of math facts. And just kind of, sometimes we call it common sense, you could solve them. Some of them are a little trickier. Let's start with number 1. 1,000 minus A equals 400. So this is one you might be able to solve on inspection. If you take 1,000 and subtract some number, you're left with 400. So some of you may be able to just reason, well, I know that if I take 1,000 and I am left with 400, I must have subtracted 600 because 1,000 minus 400 would leave 600. So I'm going to say A, I believe, equals 600. And then I can check down in my solution bank, and I see it's right there. But the way to check this to see if I've done it right is to actually substitute what I believe the solution to be in for A and see if I get a true equation. So if I substitute A for 600, 1,000 minus 600 equals 400. Is that a true statement? Is it a true equation? Yeah. And that's kind of one of the nice things in what we're getting into here in pre-algebra, is that you can always check your solutions when you're trying to solve an equation by substituting it back into your problem and seeing if it makes the equation true. So here we go. Number 2, 10E, and again, this means 10 times E, is equal to 1. So again, some of you might be able to figure this out without doing any pencil and paper work. But if I was thinking about this, 10 groups of something equal 1. So if I wanted to try using this, a tape diagram to solve this, I've got ten groups of E have the same value as 1. So to solve this, I would have to do 1 and split it into 10 equal groups. So I would be doing 1 divided by 10. And 1 divided by 10 is 1/10, or if I want to write it in decimal form, 0.1. So if I come down to my kind of number bank here, and there I see it, 0.1, 1/10. All right, coming back to question 3. 12.6 has the same value as equal to B plus 4.1. So some number plus 4.1 equals 12.6. Some of you may be able to reason, well then, if I take 12.6 and subtract 4.1, that should leave the value of B. So 6 minus 1 is 5. 12 minus 4 is 8. So I believe B is going to equal 8.5. And then I can substitute it back into my equation and see if it's true. Is 12.6 equal to 8.5 plus 4.1? And I can kind of do this in my head. 8 and 4 is 12. 5 and 1 is 6. So yeah, I get 12.6 is equal to 12.6. So it checks. And then I'm going to come down here, make sure it's actually one of my possible solutions. It's right there. So I'm good. Let's choose a different color so we don't get running together. All right, h plus 3.3 is equal to 1. So again, I've got two numbers combined equal a third number, and I don't know what number h represents. Well, similar to this one, if I've got two numbers combined equaling a third number, I should be able to find my unknown by subtracting 3/7 from 1. So I could say 1 minus 3/7 is going to equal my unknown h. If you remember when we were adding and subtracting fractions, I can change to subtract or add, they need to have the same denominator. So I need to change 1 into an equivalent fraction that has a denominator of 7. So I'll make it 7/7 minus 3/7 is equal to h, and 7 minus 3 is 4, so I come up with 4/7 is equal to h. I can look down here and see, is that one of my options? And it is. And now I'm going to substitute that into my original equation and see if I get a true equation. So if I substitute 4/7 in for h and add it to 3/7 to see if I get 1, well, 4/7 plus 3/7 is 7/7, and 7/7 is 1. So I get 1 equals to 1, and I have a true statement, a true equation. So I could check my answer. All right, 5. 8 times c equals 8. And again, this is one, most of you can do by inspection. 8 times some number equals 8. And the only value of c that could make that true is if c equals 1. And I can check that. If I substitute 1 in for c, I get 8 times 1 equals 8. So I have 8 equals 8. It's a true statement. And then I can come down here and see, do I find 1 as one of my options? It's right there. All right, number 6. 10 is equal to 5/10 times f. So this is one that could be a little tricky if you're trying to solve it by inspection. Sometimes you got to think about what multiplication means. I know that the equivalent fraction to 0.5 is 1/2. So I could also think of this as 10 is equal to 1/2 of f, 1/2 times f. Well, if half of some number equals 10, then that whole number must be twice as much as 10. So if 1/2 of a number is 10, that number must be 20. Because 1/2 of 20 would be 10. I can come down here and see, is it in my bank? Yes, it is. And then I can go ahead and substitute it into my equation and see, when I evaluate it, is it a true equation? So is 10 equal to 0.5? And now I have to, I can't just put two numbers next to each other to show multiplication. I've got to use some symbols, either brackets or a multiplication dot there. 0.5 times 20, or 5/10 of 20 is 10. So I get a true equation. All right, number 7. 2/3 times d equals 10/9. So this one's a little bit trickier. We have to kind of think about, these aren't numbers that are in our math facts, so we might not be able to just immediately see relationships between the numbers. But what we can do is look back at how we solved some similar problems that used kind of whole numbers. Let's see. 2/3 of d is equal to 10/9. So let's see, how do I want to do this? Well, I could use just some reasoning. if 2/3 of D is equal to 10/9, 1/3 of D is going to be half as much, so that would be equal to 5/9. I just said 2/3 is 10/9, so 1/3 would be half of that, which would be 5/9. 10/9 divided by 2 is 5/9. So then D is going to be 3/3 D. We know 1D is going to be equal to 3/3 D. So that's going to be equal to 3 times as much would be 15/9, because 3/3 is just like saying D, 1D. So just using some reasoning, D is equal to 15/9. Do I see that down here? It might be written in a different form. Let's see, 15/9 is going to be 1 6/9, which is going to be 1 2/3, or 5/3 if I leave it as a improper fraction. So there's my solution. All right, our last one, number 8. 99/100 is equal to 1 minus G. So if I take 1 and subtract some number, I'm left with 99/100. So if I, kind of using my rationale, if 1 minus some number leaves this, then 1 minus that number should leave that. So I should be able to do 1 minus 99/100 to find out what G is. So if I do 1 minus 99/100, come over and borrow. 10 minus 9 is 1, 9 minus 9 is 0. So I'm reasoning that G is equal to 100. And then I can substitute that into my equation to see if I get a true statement. Is 99/100 equal to 1 minus 100? So if I do 1 minus 100, and I'm going to do my crazy borrowing again. 10 minus 1 is 9. 9 minus 0 is 9. And I get a true statement. It is equal to 99/100. So I'm going to look for that in my solutions, and there it is. All right. So we solve these equations not using any sort of systematic process. We kind of used the individual problems and our own reasoning, and you could have solved these very differently. Oh man, I just realized I didn't have that. You could have solved these very differently. As we continue through this unit, we are going to work on coming up with a more systematic procedure, an algorithm for finding solutions to equations that don't rely so much on examining the individual relationships between numbers in a problem and their structure. But for now, we just want to kind of use our reasoning and logic.